To the afternoon section. So let's welcome Andrew Grigoletto from Durham to talk about the unitarity in the categorical symmetries. So let's welcome him.
Actually, or should I? Can you hear me? Yeah. Right. So first, let me thank the organizer for organizing this very nice workshop. I'm sure this week is going to be very fun and inviting me to talk today. So I want to talk about the relationship between unitarity and categorical symmetries. So let's start from the very basics. So this last few years, we've seen a ton of progress in the study of symmetries in quantum field theories because we started to really appreciate the fact that the notions of symmetry in quantum field theory should be identified with the notions of topological defects that systems may exhibit. And in fact, we've seen a lot of interesting phenomena on this regard, and I'm sure we're going to see a lot of talks about this for the rest of the weeks, and also like for the talk that we heard this morning. And a lot of the focus so far in trying to understand better this kind of symmetries was focused on trying to describe their fusion structure and the implications that arise because of this. Today, I want to talk about unitarity, which is one of the more basics, if you want, aspects that we know symmetry should behave. We are very used to think about unitarity as a property in terms of symmetries in a traditional sense, that we think about unitarity as, for a group like zero-form symmetries, as the fact that this symmetry should be represented at the level of Hilbert spaces by some unitary operator, so that needs to satisfy some equations like u dagger equals to 1. And this traditionally has been very, very important in trying to uncover non-trivial constraints for symmetries in quantum field theory. For example, it can be used to probe a relationship between the spin and the statistics of particles. It can help us to define the classifications of anomalies, to put constraints on the properties of fields that you may have on QFTs, and so on. However, if we try to apply at face value this kind of notions of unitarity for non-invertible symmetries, we immediately come to some incompatibility. And this is simply because of the very notions of non-invertible symmetry, which do not allow to have an equations like this to be satisfied. So there is this kind of incompatibility, and the question is, how can we actually resolve this? Because unitarity is one of the few things that we know is extremely important in quantum field theory, and we don't want to give that away that easily. We know there should be some sort of way to resolve this thing, simply because we know that non-invertible symmetries are peculiar in the sense that they start to mix various twisted sectors of your theory. So there should be some way we can make precise the notions of unitarity for this kind of symmetries. So this is one of the questions I want to try to address. And to try to address this, I want to think for the rest of the talk about topological defects as being TQFTs in general, simply because if we think about TQFTs, then we have a lot of tools that comes from the topic that we can actually use to, in principle, define the notions of unitarity. But it's important to remember that if we try to build a connection between TQFTs and symmetry defects, we need to think about these TQFTs and not just TQFTs in a vacuum, but we need to think about them as satisfying some additional properties that represent the fact that these are embedded into some higher dimensional system, and of course that are fully extended. And assume that we are able to make these kind of things precise, then another natural question is, what can we say by these kind of properties? So the rest of the talk is going to be divided in the following ways. First, I'm going to try to give you an idea of what should be the correct notions of unitarity for this kind of symmetries. I'm going to try to build it from low dimensions first and try to sketch, at least, what should be the generic structure in higher dimensions. Then I want to give some application in terms of solitonic symmetries and how unitarity enter the picture in these examples. And then I want to talk about a conjecture about the possible relations between unitarity and stability for this kind of symmetries. Let me say that for the rest of the talk, I'm going to assume that we are in Euclidean spacetime. So for me, the notions of unitarity will be equivalent to that of reflections positivity. So let's start to describe the notions of unitarity in some cases where we actually know what that means. So let's start from the easiest possible example, which is try to describe group-like symmetry of a quantum mechanics system. Well, what we learn in the undergrad, right, is that the notions of a symmetry is given by having a bunch of operators which commute with the Hamiltonian. These operators are going to act on the operators of your system via conjugation. And the important thing that capture the notions of unitarity in your quantum mechanical system is the fact that these operators are represented unitarily. So again, to satisfy the equation of before, you have u dagger equals to 1 up. And the composition can be, of course, defined up to some projective phase which capture the anomaly. Now, unitarity is stored at the level of the algebra that's generated by this kind of operators by saying that this algebra is a sister algebra, which literally means that we have an involution, and that's compatible with the norm that this algebra gets by thinking about these as operators acting on a Hilbert space. Now let's try to rewrite these in terms of TQFTs. And of course, we want to think about point-like TQFTs embedded into a line. These are going to be labeled by your group elements, and the fact that these are points embedded into a line, it means that whatever the structure is that capture these things, we're going to have some particular properties. First thing is that if we think about these as being sort of TQFTs, this can be defined on points, which can have a stable orientation, which literally means that we have an orientation on the line, and the structure that we have on the point is just the pullback of the structure that you have on the line. Then, since we want this to be topological, we can in principle move them along the line, and we can fuse them together. So it means that the vector space generated by the linear combination of these key TQFTs is going to be an algebra. And the fact that we have an algebra, since I'm going to want to work with categorical symmetries, can be described by the fact that we can actually deloop it and rewrite it as a category. So instead of thinking about the algebra, I want to think about one category with a single object, which you can identify with the Hilbert space of your quantum mechanics. And the endomorphism of such objects are going to be identified with your algebra of symmetries that act on it. Now, how do we then capture the notions of unitarity? Well, at this point, we're not saying anything particularly deep. We know that the notions of unitarity at 1D is described by having the algebra to be a sister algebra. We just want to give the notions of a sister algebra to represent it in categorical terms. So then it's easier to generalize it in higher dimensions. And the way we do this is by saying that BA is a unitary category, which means that your endomorphism of your algebra, of your category, has an involution, have an involution. And since this is going to be a linear category, we ask this to have a compatible norm with the involution. Again, just said in other terms, what's the notions of a sister algebra? So this is the easiest example. We can get also some other kind of example of unitary category. We can think, for example, of the one category of finite dimensional vector spaces, Hilbert spaces, sorry. So we have a positive definite remissions metric and maps between them. We can think about this category, for example, which is now a version of this with more than one object, as a category which captures multiple TQFTs, where the endomorphisms are just the topological operators that sits in this kind on each of these TQFTs. And the homomorphisms from different objects are just domain walls between these different TQFTs. All right, this is how we capture unitarity in 1D. Let's now try to do it in 2D. In 2D now we want to think about one-dimensional TQFTs and zero-dimensional operators in it. So we're going to expect to have a one category precisely for the reasons I said a second ago. And this is going to have a bunch of properties. So we now want to capture topological deformations in 2D. And this means that we're going to have additional properties for this category. The least amount of properties we're going to require are represented by requiring deformations that preserve a framing. That's usual lore in TQFTs. The more data you're requiring your manifolds to have means the less data your category is going to have. So what's the kind of data we need to require to have such an embedding? Well, first of all, we're going to have a composition as earlier, which means that we can actually deloop it again. We're going to have a two category with one object. And then since we have to think about the objects to be describing lines with a framing, then this means that in general, we're going to have two possible framings on lines, and they can be connected from one to the other via some kind of morphism like this. All of this structure together is just a way to say that your C has dual, or equivalently that your delooping has adjoint. And this means that eventually, by assuming that this is linear, you're taking linear combinations of your TQFTs, this is just a fusion category. And now, how do we include unitarity? Well, the way we include unitarity is by requiring these TQFTs to be unitary in the first place. And you can see that this will be compatible with the frame embedding. In 2D, however, we are not just used to work with frame TQFTs, we are used to work with oriented TQFTs. So we haven't asked for all the possible deformations our topological defect should be invariant from. In fact, we have another kind of deformation we should be worried about, which is the fact that if we start from a defect with a particular framing, and we do a 2π rotation, we ought to go back to the original framing that we are supposing our line to have. This, in categorical terms, means that we are asking to have a natural transformations from the identity of your fusion category to the double dual. And this is called, this says that C is a pivotal category. And now we should actually make sure that the notions of unitarity, which at the level of 2D is encapsulated by reflections positivity, is compatible with this kind of transformations. So if we worry about the reflection that capture reflections positivity, this should also affect our topological lines. And we should make sure that the reflection is compatible with the kind of topological deformations that we can do on the line. So we should require to have some compatibility between this kind of deformations and the reflections, which at the level of the line was captured by requiring to have a unitary category, which also should imply some further conditions, which can be figured out to be the fact that your pivotal structure is identified by something like this. All of this structure together means that your fusion category is unitary, pivotal, with unitary duals. You can do some sanity check just to be sure that what we get, the implication we get by asking something like this makes sense. For example, we're going to find that the dimension of your simple objects in this fusion category are positive by asking for something like this. Now, I just told you that we expect that the notions of unitarity is given by having some additional conditions at the level of your fusion category. So then what does it mean for these categories to act unitarily? Well, I said earlier that this means that there should be some sort of unitary notions of the representation theory of these symmetries, which now is going to act on different twisted sectors. So the representation theory of non-invertible symmetry is described by what we call tube algebras. The idea is the following. We start to look at various twisted sectors that your theory may have on, say, on S1. So here is twisted by some line vertical to it. And we start to act on this Hilbert space by the defects of your fusion category. This in general gonna give you mix various twisted sectors. And the kind of representation theory that describes these sort of things is the representation theory of what's the so-called tube algebra. So how do we capture then the notions of the fusion category to act unitarily? Well, we interpret the notions of this fusion category to act unitarily as the fact that this algebra is a sister algebra. If this were a group-like, it's not necessary that mix different sectors, but it will still be a sister algebra. The fact, once you start to include non-invertible symmetries, then you're going to have a mixing between the various twisted sector, but the property of the C-star of this algebra to be C-star still remains true. And we can try to look, for example, for this particular example, to label the various irreducible representations that mixes the various sectors. And we're going to indeed find that these various representations are precisely C-star representations. And this is the way we interpret, at least in 2 dimensions, that a non-invertible symmetry acts unitarily. So now let me just quickly sketch what should be the generic structure, if there are no questions. So what I just tried to tell you is that the notions of unitarity for non-invertible symmetry just means that your fusion category or higher fusion categories are equipped with some additional data that depends eventually by the dimensionality of your system. However, what I just told you is definitely not the generic case. First of all, I just told you how it works in 2 dimensions or 1 dimension eventually. And then I just told you how it works when you have an orientations. And now we really like to have a notions of unitarity, which may work for more generic systems, say for system which has fermions or time reversal invariants. Furthermore, there is another problem, which I haven't mentioned, which is more technical, which is the fact that the notions I told you before are data that your category can be equipped with, which are not very well behaved in categorical terms, because they are defined a bit ad hoc from the case you're trying to work with. And this makes it very difficult to make some generic statements. So in trying to give you the generic notions of unitarity for higher form symmetry, first let me try to introduce what's the notions of a symmetry type. Well, as I said earlier, if we just have bosons, the standard thing we say is that our QFT can be defined over oriented manifolds. And if we instead require to have fermions, for example, we require our manifolds to have a spin structure and things like that. This kind of things are captured by a symmetry type, which describes the sort of tangential structure that we are assuming our manifold to have, on which we allow our QFT to be defined on. And the symmetry type is given by a couple, rho and H. H is the group, a Lie group, which describes the sort of generalized rotations that I can do at the level of the tangent space of my manifold. And rho is just a map that goes into O, which tells me how these are mapped into the actual rotations of the tangent space. So whenever we want to talk about reflections positivity, this kind of symmetry type, which again defines the generalized rotations that I can do over my manifold, can be lifted to a H hat structure on my manifolds, which is literally an extension of these rotations here with an additional Z2 symmetry, which is the reflection, which I use to define the notions of reflections positivity on a QFT. And there is also a technical statement about the kind of symmetry types I want to work with, which are essentially symmetry types that I want to be good enough such that they can be defined on any possible manifold on any possible dimension. So, for example, the orientation is something I can define for any manifolds of any dimensions, spin structure the same, and so on. So, all right. So, sorry. So just to give you an example, when we're talking about an orientation, H is SO, and the extension that includes also the reflections for which we're using to define reflections positivity is given by ON. So the full orthogonal group. Now, as I showed earlier, the notions of unitarity can be seen as giving a sort of SO hat data. What does it mean? Well, if n is equals to 1, we were in 1D, it means that, well, this is trivial. Besides the reflection, this is just a Z2 data. If this was SO2, then we will ask for an O2, which was the kind of data we asked for a pivotal category with unitary duals. We had the reflections and the invariance under rotations. And we asked to have this data on some n category with adjoints. Now, the fact that we ask to have some data on some category of adjoints is not a case. In fact, from category theory, we can recover that n categories with adjoints can be seen precisely as a way to represent topological defects in n dimensions, which are framed. This is precisely the first thing we assumed when we asked to have a framed calculus of topological lines in 2 dimensions, right? And it turns out that it is something that holds in general in any kind of dimension. So we just require to have a category, in principle, with just one object that had adjoints. And this is precisely a good way to have a graphical calculus of frame defects. And then we also asked to put some additional data on it, right? Well, in category theory, as a general rule of thumb, we know that whenever we have some additional data that should represent some invariance under some particular structure, well, this data comes from looking for some homotopy fixed point of some action of this structure on whatever you're trying to work on. Indeed, this is precisely the case that it works for the data that we asked earlier. So as a particular example, as a particular example, when we ask the category of Hilbert spaces to be unitary, well, it turns out that we actually did a bit unconsciously required for some homotopy fixed point with respect to the involutions, with respect to the reflection on a line. And that's precisely part of the data that you need to require in order to define a unitary category like Hilbert C. It actually turns out that you need to require a bit more. You need to not just require the notions of reflection, you need also to require the notions of reflections positivity. So you need to make also some positive choice. So you need to add some additional data in, which is described by requiring some flagging as some kind of big commutative diagrams like this. But it's a way we can actually rephrase in categorical terms the notions I showed earlier. Now, why I'm presenting this? Because this kind of way to describes unitary categories with unitary categories in 1D can be generalized in any dimensions, precisely because, as I said earlier, we have that n categories with adjoints are a graphical frame calculus over Rn for any dimension. So we can do the same thing as I just did for Hill in any dimension. And this O2 describes the notions of unitarity with respect to SON for higher categories. So for higher fusion categories, for example. Not only that, but we can actually adapt it for generic tangential structures. Well, here there should be a hat here. As long as we use the homomorphism that we are naturally equipped with from the tangential structure we are interested in into ON, which we now see as the rotations that are associated to our category with adjoints. So this is a way we can make precise, in principle, a notions of unitary Higher fusion categories. So in particular, we can figure out a way to describe this kind of data, say in 2 dimensions. This is going to correspond to having a bunch of maps and a commutative diagram in general between such maps. And this is the case, for example, for having a fusion category, which is unitary pivotal with unitary duals. Things start to get a bit messy. I don't want to get the details about this. If you want, we can discuss it later. But I just want to give you a taste of the fact that there is a formal way to embed unitarity at the level of your categories which encodes symmetry defects. So what's the point? The point is that, well, if we are in n dimensions, we are going to have that our Higher fusion categories, in order to be considered unitary, should be equipped with some H hat D dagger structure, which is a structure similar to what I just sketched the slides before. And the way we can understand it is that we are sort of treating our defects labeled by your fusion category or Higher fusion category as describing unitary defects over a unitary, almost trivial d-dimensional TQFT. Now, why am I telling all of this? Because the expectation is that once we start to have this kind of notions of unitarity, we expect to be able to define a notions of unitarity at the level of the representations of this Higher fusion category. So as we said earlier, for example, these notions of H hat dagger allowed us to get a C star notions at the level of the representations of a fusion category. And the same things we expect to hold true in higher dimensions. So for example, we can actually check that irreducible representations of 2 groups in 3 dimensions generate something similar. In this case, it's still going to generate an algebra which labels the irreducible representations of point-like operators. And again, we can find that this algebra, which labels your representations, is again a C star algebra. And this is precisely by requiring your fusion category to have the correct notions of being H hat free dagger in this case. This is the kind of expectation. I barely scratched the surface just to give you a taste. And if there are no questions, let me try to talk about some applications on solitonic symmetries. So let me give a brief comment first, which is that so far, when we work with Higher fusion categories in higher dimensions, we used to make a lot of comments. We used to work a lot with categories like n-vect or ns-vect and try to look for functors into that or something like that. Now, if we try to care about the notions of unitarity, then we should realize that this is not actually the way everything should work, because the notions of unitarity should take into account the fact that this category should be equipped with some additional homotopy fixed point data that describes the fact that your defects can be deformed with respect to, say, orientations or spin structure and things like that. Furthermore, in general, we have that this data may depend not only by the dimensions of your TQFT, but also the total dimensions on which you're trying to embed your defect. Are there any? Okay. So in general, if you want to be extremely precise about how to incorporate the notions of unitarity for non-invertible symmetries, we should expect to replace this kind of notions of higher vector spaces and things like that by some higher notions of Hilbert spaces, which are going to depend by your tangential structure. and in principle by the dimension and the codimensions of which you're thinking these defects to have. Now, let me give you some very basics example and try to look, say, at what happens when you look for defects which are oriented. Well, this means that depending on the dimensions you are trying to work in, we are going to have a different structure your category is going to be equipped with. So if we try to think about oriented TQFTs which are unitary, embedded in 1D, so in a vacuum essentially, this means that we are thinking about HILT as just as a unitary category. If we think about it as being embedded into 1D, this means that we're going to think about a unitary fusion category, and so on. Nothing particularly relevant happens besides the fact that you're going to have an additional structure given the fact that you are thinking about either lines in 2D, lines in 3D, and things like that. So nothing very particular. Interesting. However, if we start to go to higher dimension, so the defects of higher dimensions, things start to get a bit more interesting. So let's try to look at the case of two-dimensional oriented TQFTs that we want to think about oriented defects embedded into some higher dimensional quantum field theory. So if we think about just two-dimensional TQFTs on their own, well, this is a classic result. The classifications of this is just given by symmetric C-star Frobenius algebra, where C-star encodes the notions of unitarity for this defect. But now if we want to think about this defect as being embedded into higher dimensions, we're going to recover that actually the classification is different, because not all of these TQFTs can be equipped with the correct notions of unitarity in higher dimension. And in particular, what it turns out is that in 3 dimensions, 2+1, the TQFTs that are good enough that can be understood as two-dimensional defect in 3D are the ones which are special. What does it mean? It means that we are practically fixing the Euler term of these algebras to 1. How do we understand this? Well, the way we understand this is that two-dimensional unitary oriented TQFT, in principle, do not need to satisfy any consistency conditions if you're just thinking about them on their own. Instead, if you start to think about them as being embedded into 3 dimensions, they need to be invariant under SO3 deformation, right? And this is something that do not work for the Euler TQFT. The Euler TQFT is an invertible TQFT. So we should ask that, so suppose we are thinking about the Euler TQFT as being embedded into in 1 dimension higher and is supported on a sphere. We should ask that the partition function of your theory need to be equals to the partition function on a point, because precisely this is an invertible defect, so we should be able to make it collapse down to a point. And this is something that is not satisfied by the Euler TQFT. So again, we see that by requiring some appropriate unitary structure with respect to, in this case, 3 dimensions, say, instead of 2 dimensions, some TQFTs need to be thrown away. And this is kind of important, because if you try to think about what's going on here in this picture, this is precisely the kind of deformation we need to worry about in order to be able, in the first place, to define the action of a defect on some local operators. So it's literally saying that the Euler TQFT is not able to be understood as a proper symmetry precisely because it cannot act properly on local operators. All right. So let's now try to look at how.
Excuse me, so even for non-invertible symmetry, this kind of equality between sphere and point are required?
In principle, no. Yes. Precisely because you would expect that you get the dimension, right? And in principle, this can be different from 1, precisely for non-invertible. If we think about, say, non-invertible TQFTs that can be recovered by some solid tonic symmetries that we'll later see in a second. This For the invertible one? Well, yes, the Euler we know it's an invertible TQFT, so the dimension should be equals to 1. For the non-invertible one, we are not going to require it to be equals to 1. But say, suppose that the dimension were an integer, then you can actually think about this integer as labeling as, we will see in a second, that the integer, if we have a non-invertible symmetry, which dimension is an integer, this can be understood as labeling some sort of functor from a groupoid with a pi0, which is different from 1, into, say, back or the correct notions of that, as we'll say in a second. And yeah, and then you can recover some similar constraints for non-invertible symmetries as well. So having given this kind of appetizer for how it works for symmetries without any additional structure, let me now just discuss solitonic symmetries. Yes? The product? There should be well, the way I'm familiar with, as requiring the notions of special, is in thinking in terms of the trace of the Frobenius algebra. And there you're just literally fixing the trace to be equals to 1 for the identity, essentially. I do not quite remember on top of my head how to the coproduct. Well, it should be.
I see. Okay, okay.
Yeah.
Okay, I see. Thank you.
So, okay, let me now just briefly talk about solitonic symmetries. Well, what are solitonic symmetries? Well, solitonic symmetries are symmetries that are able to prove, not prove, topologically non-trivial configurations of, say, some sigma models with a target X. And they are described by TQFTs that can be thought to be correctly coupled to your target of your sigma model and then embedded into D+1 dimensions. The recent classification, well, the original classification was supposed to be given by looking at the various homotopy groups of your target X. This was the old classifications, very similar to the arguments that were used to classify non-perturbative anomalies back in the 80s, I guess. In the last few years, there's been like a revamped notions of what should be the correct classification of this. In particular, was precisely suggested by you guys in the audience. And the thing that was made clear in this paper is that the old classification in terms of homotopy groups were not the correct one, because we weren't actually asking the full topologicalness of the defects that should describe our solitonic symmetries. Instead, by requiring a full topological invariance of these defects, we arrive to the suggestions that the solitonic symmetries should be labeled by looking at functors of the groupoid of that represent your target into the correct notions of dvect or dsvec, assuming whether you were interested in bosonic theories or fermionic ones. And in particular, in these works were pointed out that we should always recover as the invertible part of these solitonic symmetries, a classification in terms of cobordist groups. Now, if we want to actually include unitarities, then we should actually replace, well, there shouldn't be an n here, sorry about that. We should replace the correct notions of the vector spaces, as I said, to the notions of Hilbert spaces, which captures also the unitary data that your TQFT that you're using as target of your solitonic symmetry should have, right? And And we suggest that this should be the correct way to describe it. Yeah. You're looking at functors from your. Yes, there is for groupoids. There is always a canonical one, and then you're looking. Yes, there should be a dagger here. Yeah, you're looking at dagger functors. So the suggestion is that they should be the correct notions if you want to really care about unitarity. So let's try to look at some basics example, very easy one. We just want to look at solitonic symmetries that describe the magnetic symmetry of gauge theory in 3D. So in this case, we understand the gauge theory as a topological sigma model with this target. Now, this target is described by this kind of homotopy type with a non-trivial action of dz2 into dz4. And we can try to classify this kind of representations. This turns out to be classified by a bunch of things, some permutation action and some charter. And it turns out that the classification of these representations precisely reproduces the magnetic symmetry with its condensation defects. What? Sorry? What is the target space? BPO for k plus 2, where yeah. It's just like the easiest example where things are easy enough. It's nothing particularly deep from the physical point of view, if you want. Just to double check that everything makes sense. Now, let me say, this is something that you will have probably found also if you didn't require unitarity. I will come back to that in a couple of minutes. Keep that in the back of your mind for the moment. But let's try to compute some other example. So let me notice the following thing. At the time when the result by Chen and Tanizaki came out, there was some comments from the mathematicians working on this community, which claimed that the statement should actually work only as long as X is a pi finite space, which means that there are only a finite amount of homotopy groups which are different from 0 in your target X. And none of them is equals to Z. This is pretty restrictive as an hypothesis. We would like to work with things that are not pi finite in general in our life. And the reasons this is asked is because when we work with TQFTs, we know that these are well defined because there is a very well-known regularizations process that makes everything well behaved. And if you lose this kind of assumptions, things becomes much more problematic. What I want to suggest is that if you try to lift these notions and you just try to work with things that are not pi finite, but you remember that you should care about unitarity, you're going to recover actually something which is sensible. So the suggestion is that indeed this statement can work also for things that are not pi finite and works in full generality. So let's consider the most basic example, which we would like to describe. Again, three bosons in 2 dimensions, which are really false out of these assumptions, precisely because S1 has pi1 equals to Z. And in fact, if you try to look at the classification without taking care about unitarity, you find something problematic. You are looking for functors from BZ into vect. And the classification is going to be given by representations of Z. And this includes problematic objects, which are not very physical. Instead, if you require unitarity, then you're going to look for unitary functors. And the classifications precisely going to recover the classifications of the solitonic symmetries that we know free bosons should have in 2D, which literally means that we recover the winding symmetry. So that's good. This starts to suggest that unitarity indeed makes things well behaved and may, in principle, allows us to push further beyond the very strict conditions that mathematicians tell us we should worry about. As a further example, we can try to compute something in higher dimensions. So we can try to compute how things works for sigma model with target CP1 in 4 dimensions. And this is the homotopy type of CP1. So there is a third and a fourth. Well, yes. You have two different Z homotopy groups. And if you try to work out the classification taking care about unitarity, what you're going to recover is precisely the classification we know from physics. Even things are very non-finite here, which again is suggestive of the fact that once you start to worry about unitarity, then you can actually go beyond the strong limitations that the formalism of TQFT tells you you should have. All right. If there are no questions about this, let me spend the last few minutes trying to talk about a possible conjecture about the relationship between unitarity and stability. So what I try to explain so far, sketch at least, is the fact that, first of all, there is a notion of unitarity for higher fusion categories, which behaves well and allows us to give a notion of unitarity in terms of their representations of twisted sectors and so on. And second, I try to suggest that unitarity starts to become important if you want to get some generalizations of fusion categories to something that is continuous, which is something we should keep in our back of our mind if we try someday to describe continuous non-invertible symmetry. However, let me also say that from a physics point of view, the results we found so far in the literature were more or less correct, in the sense that so far, instead of working with the correct notions of Hilbert spaces and so on, worrying about all the additional data, we just work with VEC as VEC or the Higher versions, and we found the correct notions. So should we really worry about all this additional data that we have that describes unitarity if we work with finite symmetries? Well, if we try to compute, for example, representations, as indicated earlier, we kind of see that factoring in unitarity is not doing something very particularly relevant, besides the fact that you get some substitutions of homs into, say, C star as some homomorphism into U1. But you see, if we start to have as domain something which is finite, this kind of things should give the same result, which start to suggest that, again, if we are in a very finite regimes, the additional data that we gave about unitarity shouldn't be so relevant. So what's going on? Well, this is something that's very reminiscent of what happens also for Tooth anomaly, as we also said this morning. So for Tooth anomaly, we know that Tooth anomalies, as was said this morning, are in relationship with deformation classes of invertible TQFTs in one-dimension Higher. And what we can do is try to look at the classifications of these TQFTs with and without unitarity to see whether we can get some suggestions about why things should behave well, even if we don't impose equivariantization with respect to some sort of unitary data. So let's look at the classifications. The classification is given by some maps between spectra, which is just another way to describe generalized cohomologies. And what we find is that, well, there is no unitary data in the non-unitary version. If we start to look at unitary version, we still have no additional equivariant data that defines this kind of invertible TQFTs. Instead, it's a non-trivial result, proved first by Friedrich Hopkins and then by Yamashita and Yonikura, is that the notions of unitarity that you should have if you are trying to classify invertible TQFTs can be completely traded off by requiring a stability of the tangent space of your manifolds on which you are defining your TQFTs. And this should be very reminiscent of what was happening when we threw away the Euler TQFT and when we said that this was not a good symmetry defect. So let's try to compute some cases about the classifications of invertible QFTs. We can try to look at the perturbative part and the non-perturbative ones and see what are the difference. If you try to look at the classifications of TQFTs which are continues with and without unitarity, we're going to find a difference. And it turns out that this difference is actually a relevant difference in the sense that requiring unitarity is doing something very non-trivial. This is very much the same thing we had when we require unitarity and we recover the correct classifications of the winding number for the free bosons. Instead, if we try to look at the classifications for non-perturbative, so something which is discrete in a sense, we find that the difference with and without taking care about unitarity happens in very specific circumstances, which is essentially when we require our tangential structure to be the k level in the white-hat tower of the orthogonal group, and we are requiring the dimensions of your TQFT to be less than the level k. What does it mean in practical terms? It means that when we are asking to have things that are not stable, so that are not unitary, the kind of structure we are asking our manifolds to have is literally a framing. We are not asking additional structure. Instead, when we are asking unitarity, so we are asking about stability, we have a well-defined notions of the tangential structure we are interested in terms of the stable tangent space of your manifolds. So, for example, what's this kind of difference? Well, in this case, in one dimensions, the TQFT that is not captured by unitary by the unitary version and is captured by the non-unitary one is literally C01, where this is the fermionic grading, understood as a bosonic theory. This is obviously something that do not behave well, and there is no reasons why we should think about it as an oriented theory, right? But in one dimension, we know that orientations are equivalent to a framing. So in principle, from Worley definition point of view, there is no reasons to throw that away. But instead, from physics argument, we know that this should not be a good unitary TQFT. So how can we recover the notions of TQFT that are just described by, say, vector spaces rather than super vector spaces as good bosonic theories? Well, it turns out that the existence of C01 as a bosonic theory comes from the fact that you're using as target of your TQFT the universal target of one-dimensional TQFTs, which is literally the target, the most generic target that you can possibly put in trying to define a TQFT like this. Now, if we try to look at the automorphism of this kind of category, what we find is that this is essentially the stable orthogonal group, okay, truncated because of the dimensions of the category you are working with. So if you really want to recover, say, vect, when we want to think about bosonic theories, it turns out that we should think about theories in S-vec which are fixed with respect to an action of SO. But now we are talking about the stable version, not the unstable one. And this, we know that is expected to give rise to the actual good bosonic TQFTs that should emit an SO dagger structure for any kind of a dimension, which literally means the good TQFTs that can be thought as defects in any kind of dimension with the corresponding unitary structure. We can ask whether this kind of thing happens more in general. We can give a statement up to dimension 2 and try to compute homotopy fixed point with respect to more generic stable tangential structure. And the results up to dimension 2 really suggest that by looking at the homotopy fixed point of this kind of stable versions of your groups precisely corresponds to describing TQFT that should be lifted and admit some sort of unitary structure. Not only that, but if we try to look at this kind of stable homotopy fixed point, we are actually quoting out TQFTs like the Euler one, which are sort of unstable, which are not invariant under the formations of their stable tangent bundle. So what we expect is that in general, this should be something that holds in general, so that if you try to compute H fixed point, these are expected to represent TQFTs that are equipped with the good structure over unitary structure over the stable tangent bundle. Therefore, what does it mean? It means that we actually expect that as long as we are worried about the description of finite symmetries and local system for finite symmetries in dimensions less or equal than 3, we expect that the local systems of unitary HTQFTs can be rightfully replaced by the correct notions of VEC as VEC and so on, which literally means by looking at the fixed point of the correct universal target for TQFTs with respect to the stable versions of your group. And this is particularly nice, as I said earlier, because this we expect should correspond to representing an invariance of your TQFT with respect to the formations, not only of the tangent space of the manifold in which they are supported, but with respect to the formations that affects the whole tangent space that you will get by thinking about your defect as being embedded into higher dimensions. And this literally means that this is why we expect that this kind of fixed point should be good local system to be used to describe symmetries in higher dimensions. So I guess my time is up. So let me just conclude. I tried to sketch that there is a notions of unitarity for non-invertible symmetries, and that this can be indeed made compatible with their representation theory. And I tried also to show that there is some natural way to include generic tangential structure for higher fusion categories, which encodes also the notions of unitarity, and that classification results may vary if we don't really care about it. And we try to go beyond the pi finiteness assumption. There's a lot that needs to be done, a lot of details that need to be figured out in full generality. And in particular, it will be very interesting to try to make precise the claim about the relationship between stability and unitarity for non-invertible symmetry, because this would give us the ability to eventually formalize a sort of notions of generalized cohomology that was mentioned this morning, also for non-invertible symmetries, and try to figure out, of course, also how to describe these kind of things from a symmetry TFT perspective. I think that's all I had to say. Thank you.
Okay, thank you, Andrew, for your wonderful talk. So since the time is limited, so just one question. Let's just do one question. So, okay, so please.
Okay, this is just a basic question, but I just want to check that there's no caveats. So for invertible phases, we know that they're captured by Anderson dual Bordism groups. So I think one of the statements here was that, so for unitary invertible phases, it suffices to just work with Pointryagin dual Bordism groups.
Sorry, can you?
So for unitary invertible phases, it suffices to work with just Pointryagin dual Bordism groups. You don't have to work with the Anderson dual.
Yeah. For the isomorphic classes. Yeah.
Is it obvious?
Well, plus the Euler TQFT, essentially. So you get the stable plus theories which are unstable from that point of view, but which are still unitary.
I see. Okay. So
it's literally this, sorry.
Right.
So for oriented, this is literally the classification you get.
Is it obvious that Pointryagin dual groups are in general subsets of Anderson dual groups? Is that obvious from the math definition?
Well, they're not subgroups. Well, here you don't have distortion, right? If you're using the Anderson dual, you do have distortion.
But shouldn't the set of unitary invertible phases be a subset of the set of?
Yes, it's a subset. Yes. These are a subset. Well, there is a map.
Okay.
So, well, yeah. These are capturing the torsion part of this bit here.
I'll ask you later. Thank you.
It's not very, yeah. Are you thinking about something? Okay.
I'll ask you again later. Thank you.
Yeah, okay. If you have further questions, please come to Andrew during the coffee break. Yeah.